through sections 9.1 through 9.3. In these sections, we're going to talk about two different kinds of acid-base theories, as well as how to name acids. Now, as we go through this, I would strongly encourage you, if you have the ability to print out the slides that are in Canvas, to do so. And then you can take notes on those slides. Otherwise, definitely have a notebook, pen, paper, calculators, and a periodic table with you so that you can take notes as you go through this video. You will still need to read the slides on your own, and you will need to read the textbook. I will be posting a suggested reading schedule for the textbook on Canvas as well, with some dates to kind of just keep you on the right track without getting snowballed. The resources in the extra help section on Canvas are going to be really, really crucial that you use these as we move forward through our remote learning. So the first type of definition of an acid and base that we're going to talk about is the Arrhenius definition. And this was one of the first definitions that was made up for acids and bases. And the Arrhenius definition of an acid is any substance that provides hydrogen ions, or H pluses, when it's dissolved or dissociated in water. A base will be any substance that makes OH, or what we call hydroxide ions. Remember, this is on your your polyatomic ions chart. Hydroxide, OH minus, when dissolved / dissociated in water. So here's an example of each of those. HNO3, by definition, is an Arrhenius acid because HNO3, right, this is a polyatomic ion here, so we know this is that secret language. I know that you know. When I see aqueous, that really means that I have H plus aqueous and NO3 minus aqueous. So this made an H plus ion in solution. So this would be the definition of an Arrhenius acid. KOH, again, that secret language. I know that you know it doesn't really exist as KOH. It exists as K plus and OH minus, generating an OH minus. Therefore, this is an Arrhenius base. So which of the following here is the best representation of an Arrhenius base? So go ahead, take a minute, pause the video, figure it out for yourself. Here we have NaOH. As we go through all of our options here, we're looking where we will produce an OH minus aqueous when a substance is dissolved in water, which when we have an aqueous solution means it's in water. This is an ionic compound. We know that's the secret language, so we get Na plus and OH minus. You may have been tempted with number 2, but that's NH3 aqueous plus more water, and that's giving us the OH minus. So this is not the same as this. It became apparent that the Arrhenius definition wasn't broad enough. It wasn't covering all different forms of acids and bases that we were experiencing. And so we need to come up with a different definition for acids and bases. Sometimes your textbook refers to it as the Bronsted. Sometimes it's referred to as the Bronsted-Lowry acid definition. These are the people who contributed to the understanding of this definition. But we're going to move ahead and talk about this. So, any hydrogen-containing substance capable of donating a proton, and in this case we're saying can donate the H+, will be an acid. And anything that can accept that H+, will be the base. So, there's a typo here. Please make sure that you realize that this should be a two-way arrow. There should be one arrow pointing in this direction. There should also be another arrow pointing in that direction. Remember, we saw these double-headed arrows when we had our strong and weak, our weak acids and our weak bases when we were talking about electrolytes. Here we have HNO2, aqueous, plus water, yields H3O plus NO2 minus. So we don't see an H plus here, we don't see OH minus here. So this is, if we were going just by the Arrhenius definitions, this would be neither an acid or a base. But when we look at what the Bronsted acid-base definitions are, this does constitute the HNO3 as an acid because it is a proton donor. It gives up this hydrogen. Does everyone see how when this hydrogen is given up, we become NO2 minus? The water, in this case, would be our base. H2O accepts this hydrogen and becomes H3O plus. So, sorry about that. Here's the double-headed arrow that I was talking about that you should see in the previous example. So again, we want to, when we're talking about Bronsted definitions of acids and bases, what we're talking about is the proton. Where's the who's giving up the proton? Who's taking the proton? Who's giving up that H plus? Who's accepting that H plus? And remember, when we have this two-sided arrow, that means this way is one direction the reaction can run, and this is the other. So when we look at that, we already said, okay, NO2 is our acid because it can give up the hydrogen and become NO2 minus. And water, H2O, can be the base because it can accept a hydrogen and become H3O plus. Now let's pretend that this is the reaction that's going. We're going to go from this direction to this direction. H3O plus can give up one of the hydrogens and become H2O. So on this side of the reaction, H3O plus is the acid, and NO2 minus will accept the hydrogen and become HNO2. So on this way, when we're going the reverse direction, H3O plus is the acid, and NO2 minus is the base. This is an important concept that we call conjugate acid-base pairs or conjugate acids, conjugate bases. And sometimes, not sometimes, in an equation where we have this two-headed arrow, this is called an equilibrium equation, we start with the right-hand side because we read from right to left. So this direction that we're going, this would be the forward reaction, this would be the reverse reaction. So we say the Bronsted acid and base are on the forward reaction. The conjugates of those will be on the reverse reaction, okay? That's just kind of a convention we're going to use. So you should be able to identify in the forward reaction who's the acid and who's the base when you look at it. Who's going to give up the hydrogen, who's going to accept the hydrogen. And then we can look at the reverse reaction, the one where we're going from left to right. And when we look at that, we see that we have our H3O plus has become the acid. So we call that the conjugate acid because the H3O plus, or the parent of the H3O plus, right, in the forward reaction was the H2O. So it became an acid once the forward reaction happened. So it becomes the conjugate acid. And the NO2 minus becomes our conjugate base. So you will have to be able to look at chemical equations and be able to identify who's an acid, who's a base, who's the conjugate acid, who's the conjugate base. And the last thing that goes with this is conjugate acid-base pairs. Basically, that's just the color coding I did here would be identifying it. The acid to the base pair and the base to the acid pair. Okay, that this is related to this, H2O and H3O plus are related to each other. And that the HNO2 minus, or excuse me, the HNO2 and the HNO2 minus are related to each other. So let's look at it with a new equation. We're going to go through and identify all the Bronsted-Lowry acids, bases, and acid-base conjugate pairs in the reaction represented below. So again, remember we have this equilibrium equation, this two-way street. We have the forward reaction, and we have the reverse reaction. So it's always easier to start with the forward reaction. So we're going to look at the forward reaction. We're going to figure out when we go from this side to this side, when we go from reactants to products, who gave up the hydrogen, who took on the hydrogen, so on and so forth. So I'd encourage you to pause the video here and try and solve this for yourself before continuing. All right, so when we look at this, we can see that the H from the HCl4, or the perchloric acid, is going to give up the hydrogen and become ClO4 minus. So this would definitely be the acid. If this is the acid, the water is then acting like a base. That H that was given up is being taken on by the water to become H3O plus. So this is my acid, this is my base. On this side, we have the conjugate acids and bases. Now we're going to talk about the reverse reaction when we go from this side as my reactants to this side as my products. The H3O plus will give up the hydrogen to become H2O. So in this case, this would be the conjugate acid. And the ClO4 minus is going to accept that hydrogen to become the HClO4. So this would be the conjugate base. So this is a pair, and this is a pair. These are the related pairs. So, are you able to look at these different combinations of things and determine which could be a conjugate acid-base pair? Again, I'm talking about looking at something like this and saying, would these be reasonable to be a pair? So take a moment, pause the video here, and come to a conclusion that you think is most reasonable. The correct answer here would be the H2O to the OH minus. Think about it. If the H gave up a hydrogen, it would then become OH minus. And that doesn't work for any of these other ones. NH3 does not give up any hydrogens or take on any hydrogens or anything to somehow magically become a Cl minus. That doesn't make any sense. You may be tempted to this one and say, oh, well, H2SO3 can go to HSO3 2 minus, but that would be losing 2 hydrogens. Remember, we only lose 1 hydrogen at a time. This would take 2 different processes to lose both of these hydrogens, so this is too many steps. And again, here we would be losing 2 hydrogens to go from H3O plus to OH minus. So number 4, excuse me, had a sneeze there, sorry. Number 4, the H2O loses 1 hydrogen to become OH minus. This is our best option. Try this problem. I would encourage you to pause here, read it, and come up with the best answer possible. The substance B, H3O plus, this is the Lewis structure of H3O plus, is a Bronsted-Lowry acid because it is a proton donor. This will give up one of these extra hydrogens to become H2O. When we look at this compound here, which is an aldehyde, which we'll learn about later, you might be going, well, it could give up this hydrogen, but is that likely going to happen? Remember, look at what this compound is. This is H2O with an extra hydrogen, so it has this plus here. Go back to your Lewis structures. Convince yourself, why does this oxygen have a plus? Okay? Go ahead and practice with that and realize that this hydrogen, or one of the 3 hydrogens here, is willingly ready to leave. It's willingly ready to be a donor because then we would get stable H2O back. All right, so now we're going to talk about some naming or nomenclature, which is a fancy word for kind of the rules of naming of what we call binary acids. Again, for just a little note, for our class, we're always going to assume that acids or bases are a solution, which means they're always going to have the state of matter of aqueous. Okay, so if we're talking about an acid, it should always have the state of matter be aqueous, unless otherwise stated. That should be your basic go-to for that, and the same with a base as well. So when we have a binary acid, bi standing for 2, binary acid is going to be typically a proton and some sort of anion. Okay, so it's a hydrogen and something else. So for example, HCl or HI or HBr, HF or H2S, something like that. We're going to go through some rules on how to name these. You may be familiar already with the fact that the HCl stands for hydrochloric acid, but how did we get there? So we're going to go through some rules on how to do this. So I've color-coded here. If you are having difficulty visualizing colors, please let me know so that I can adjust slides and my videos and everything like that. If I don't hear from you, I'm going to assume that everyone can visualize these colors just fine, and that we'll be using that moving forward. So if we have the compound HI, you would think, right, if you were just to name this how we typically named our our organic compounds, right, non-metal, we would just say hydrogen iodide, right? This would be hydrogen iodide. Okay, that would be the name of it if it was a compound. So if we had HI, the solid state of matter, that would be hydrogen iodide. But if we see HI aqueous, we know, like we said, right, aqueous is going to mean that it's an acid. So it's going to have a different name. The first thing we'll do is, instead of hydrogen, we're going to make it hydro. Okay? And the iodide will remain the same. So now we have hydroiodide. We're not quite done yet, though. We're going to take that "ide" and cut it off and make it "ic." So we're going to have hydroiodide will become hydroiodic. And lastly, we're going to add the word acid to the end of it. So it becomes hydroiodic acid. Okay, so we cut off the end of the hydrogen and just make it hydro, and then the iodide for whatever anion it is. This could be a bromide or something like that. We cut off the "ide" and add "ic," acid. So Hi, the acid, is hydroiodic acid. Here are those rules just written out for you that we just literally talked about. The one thing I want to bring up here is when we're talking about polyatomic ions, because we will see polyatomic ions. We saw lots of examples already of polyatomic ions in our previous slides. For example, here, this is a polyatomic ion, right? ClO4 minus is a chlorate. And so we have perchloric acid, right? So we're going to go through and describe how we go through and name acids and bases that have polyatomic ions in them. And this is the rules that's sometimes referred to as adic-itis, right? So like if you have appendicitis or something like that, it's a little joke. But it helps you memorize it. If the polyatomic ion ends in 8, we're going to replace it and end it in "ic." If it ends in "ite," we're going to end it and replace it and end it with "us." So if I had sulfate, it would become sulfic. If I had sulfite, it would become sulfus. Okay, so we're going to see some examples with that. Your homework will also be a really good practice for this. So first, let's try a really simple one. This is very similar to the example we did with the Hi. So I would like you to go ahead and name HCl, the compound, the acid. We're talking about HCl aqueous. This is what your digestive juices are. So I would encourage you to pause here and go through those steps, flip back, and try and name this compound. So we know that if it was just the compound like HCl the solid or HCl the gas, we would have hydrogen chloride. But we know this is an acid. So we're going to have hydro instead of hydrogen, and we're going to have the chloride would become chloric. So we're going to have hydrochloric acid. Here's an example of one where we have a polyatomic ion present now, right? We have phosphate here. This is not a minus charge. This was me just saying like dash, okay? So sorry if you're confused that that's a minus charge. This acid is super important in bodily functions. We'll see a lot more with it when we get to our biochemistry section. But go ahead right now, follow the rules that we have, and try and name this compound. So when we go through it, we're going to find out that, right, we have the polyatomic ion phosphate in there, and this ends in 8. So what we're going to have to do is 8-ic. 8 becomes an ic. So we end up with phosphoric acid. Okay? When we have a polyatomic ion, we don't need the hydros in there. It's understood already what we have going on. Now, because phosphorus is got kind of its own little weird rule for it. Phosphoric acid is actually something else. So Rule 5 talks about phosphorus-containing compounds. We actually name them like this. We say phosphor instead of phosphic. So this would be phosphoric acid. The rule number 5 is a very slight, just like grammatical rule at this point. So just be aware of it as you're moving through your compounds. Lastly, let's look at an example. What is the name of the acid H3ASO3? If we know that ASO3 is named arsenite. Remember, we have "ite" at the end here, so you should be able to come up with a reasonable answer for that. The correct answer would be arsenous acid. Okay. This is the end of our first section of notes and lecture slides. The next video will be on sections 4 through 6.